Okay, question 3, we've got an inductor and a resistor in series with an AC supply, so no capacitors. So the multimeter measures the current in the circuit is 15 milliamp. Okay, calculate the reactance of the inductor. Let's recall our question, our formula again. Reactance of the inductor, 2 pi FL, remember, as frequency increases, inductive reactance increases. As the frequency decreases, the reactance decreases. So let's go back to where we were. Calculate the reactance of the inductor. XL equals 2 pi FL equals 2 pi times frequency 1000 times inductance 0.45, so that equals 2800, and again we measure it in ohms because reactance is an impedance, a resistance to the flow of current. And note 2, we can only have 2 significant figures. That's why we've cut it down to 2800. So here calculate the Rms voltage across the inductor, across the resistor. Our equations again. Voltage across an inductor. Voltage equals current times inductive reactance. We've got the normal Ohm's law expression, V equals IR, and this one here, which will come with a later question, the voltage across the capacitor is equal to current times capacitive reactance. So let's apply those equations from Ohm's law. V equals IR across the resistance, so voltage across the resistor is equal to 0.015, that's 15 milliamps, times 2000 equals 30 volt, and the voltage across the inductor equals current times the equivalent to resistance in the inductor, which is the inductive reactance, is equal to current times calculate the RMS voltage of the supply voltage. Okay, we know that the voltage across the resistor is 30 volt, the voltage across the inductor is 42 volt, and we want to know the supply voltage, so we've got to add these two together, the voltage across the resistor plus the voltage across the inductor, but we can't just add, we've got to add them vectorially using our phasors. So let's perhaps have a diagram of this. We've got the voltage across the inductor of 42 volt, and we've got the voltage through the resistor of 30 volt. And remember that the voltage across the inductor, it always leads the voltage across the resistor by 90 degrees. So there's our perfect 90 degrees you can see there. So in order to add these two together, we add them vectorially, we add them, and we end up with this here is the supply voltage. And again, that will be Vs, so that's what the power source is providing, and we can do Vs equals by Pythagoras square root 42 squared plus 30 squared, so that should equal 52 volts, and again two significant figures. Part E, calculate the phase difference between the supply voltage and the induced voltage. So note that where it's supply voltage and induced voltage, it's not the voltage across the resistor, it's between supply voltage and induced voltage. So we're going to be looking at this angle here, this angle theta here, and from our triangle there we can use our trigonometry, and we can say tan of theta is equal to opposite 30 divided by adjacent 42. So we write inverse tan theta is equal to 30 over 42, which gives us theta equals 35 degrees. So we can say the voltage across the supply lags, falls behind the voltage across the inductor by 35 degrees. That's the phase difference.